The question is, could you tell us how to solve a torsion problem involving gears? Sure, yeah. Well, gears are used for a couple of different reasons. For example, gears are used to transfer power or torque from one shaft to another. Gears are used to change the direction of the rotations of the shafts. And gears are used to change the speed of shafts, right? And of course, there are various applications as well. For example, gears are used simply to transfer torque from one shaft to another. Those are the kind of problems that I will discuss here. But of course, more commonly, gears are used to transfer power from a motor to another shaft. And there, the shafts are rotating continuously, and we will not get into problems like that here. A couple of basics of gears that we need to know in order to handle problems involving gears. Now, the gears are not the only ones that are used to transfer powers and torques from one shaft to another. In addition to gear, there are friction rollers, belts, chains, bevel gears, miter gears, and so on that are available for this purpose. Here we are not really interested in the transmission of power per se. In other words, we are not interested in gears that are connected to a continuously spinning motor. We will restrict our discussion here only to the transfer of torque from one shaft to the other. So if you understand the mechanics of gears, then you will understand the mechanics of other kinds such as friction rollers and belts. Even among gear, there are several kinds such as spur gears, internal gears, helical gears, and so on. Once again, most fundamentals are the same with some differences between them. So we'll pick one kind and focus on that, namely the spur gear. Spur gears have teeth like shown in this picture. Normally one of them is a driving gear, the other is a driven gear. So for the problems we are interested in here, let's say the torque is applied on one gear and that torque is then transferred to the other gear. The two gears make contact at what is called the pitch circle. So for the purpose of the analysis, we can just forget about the teeth and then think of these as two circles that are in contact with each other, like shown in these pictures. So these circles are the pitch circles, and the radius of these circles are relevant for the analysis here. So it goes without saying there's the shaft attached to the driving gear and the shaft attached to the driven gear. So from a mechanics point of view, there are two things that are important for us here. First, a relationship among the torques, forces, and the radiuses. So for that, let's focus on this picture right here. Say there's a torque T1 applied on the driving gear. This leads to the development of contact forces, F1 on the driving gear and F2 on the driven gear. The direction of these contact forces are tangent to the circles. By Newton's third law, which is the action-reaction law, F1 and F2 must be equal to each other in magnitude. So this allows us to calculate the torque T2 that is going to be felt by the shaft attached to the driven gear. Remember, torques are moments, right? A torque equals the force multiplied by the distance perpendicular to the line of action of the force, right? Since F1 and F2 are equal to each other, let's call that as F. Then T1 must be equal to R1 times F. T2 is then R2 multiplied by F. So from the first equation is F equals T1 over R1. From the second equation, F equals T2 over R2, and therefore T1 over R1 and T2 over R2 must be equal to each other. So this is the first important relations we need to analyze systems involving gears. The second is a relationship between the angle of twist of the driving gear and the angle of twist of the driven gear. Supposing, say, this first gear rotated by an angle phi1 and the second gear rotated by an angle phi2. Since the two gears must be in contact with each other all the time, the distances traveled by the gears on the gears must be equal to each other. In other words, AB here must be equal to AC. So these are basically arc lengths, right? So what is the arc length AB? Well, R1 multiplied by phi1, right? And similarly, AC would be equal to R2 multiplied by phi2. So they must be equal to each other. So this is our second important relations. Let's go ahead and do this example problem. So this is a simple problem involving two parallel shafts AB and CD and a pair of spur gears B and C. I'm not showing the teeth here, but I'm showing only the pitch circles. The shaft AB is supported on two journal bearings, and shaft CD is supported on one journal bearing and a fixed support. If you recall from statics, journal bearings are bearings that will hold the shafts in place but allow smooth rotations, right? A torque of 2 kilonewton meter is applied at point A. So obviously this torque is going to be transferred to gear C through gear B. So you can think of gear B as the driving gear and gear C as the driven gear. Of course, there's not going to be any continuous rotations here. This gear, this shaft is fixed at point D, but there is going to be angular twist all over the place. Point A is going to twist, point B is going to twist, point C is going to twist. Only point that's not going to twist is point D because it's fixed. You can see the exact locations of these journal bearings are immaterial because they don't really interfere with the mechanics here. The mechanics is simple rotations of the shafts, right? The questions are to determine the maximum shear stress in shaft AB and shaft CD and the angular twist of point A. We do have these two relations that pertain to gears that we derived in the earlier slide. Alright, let's start working on this step by step. First, we want to find the internal torques in the two shafts, AB and CD. As part of that, first I want to find the contact force F between the two gears. We can find F simply by writing down a torque equilibrium equation for the shaft AB. That's what I have done over here. So here F multiplied by the radius is a torque in the counterclockwise direction, right? And then TA is the torque acting in the clockwise direction. So both of them put in this equation algebraically should sum up to 0. And from that we get a value of 26.67 kilonewton for F. I'm going to take this as my x-axis. Now I'm going to section the shaft AB at point E, separate that into two parts, A to E and E to B, and mark the internal torques at point E. So I'm going to mark this in the counterclockwise direction with respect to the x-axis. In other words, on this part, it'll be the counterclockwise direction. And I'm going to do the same thing at point F for shaft CD. Now considering the torque equilibrium of AE, I get a value of minus 2 kilonewton meter for TAB, and considering the torque equilibrium of CF, I get a value of 3.33 kilonewton meter for TCD. Now that we have values for the torques, we can go ahead and calculate the maximum shear stresses within the shafts. Remember, within a cross section, the shear stress varies linearly starting from 0 at the center, with the maximum occurring at the outer fiber of the cross section, right? Alright, so here first I calculate the polar moment of inertia of shafts AB and CD, and then go ahead and use the torsion formula to calculate the maximum shear stress within AB and CD. So steps are fairly easy for you to follow, and I get a value of 47.2 megapascal with a negative sign in front of that for tau max in the shaft AB, and I get a value of 33.1 megapascal for tau max in the shaft CD. Now let's go ahead and calculate the angular twists. First, let's forget about what's going on here and consider each of the shafts AB and CD separately, independently, and calculate their own respective angular twists. In other words, we take shaft AB and calculate the angular twist of A with respect to point B. And that you can do using this formula right here, and I get a value of minus 2.7 degrees for that. And similarly, we take shaft CD and calculate the angular twist of point C with respect to point D. And that's what this is, and I get a value of 0.5343 degrees for that. Our sign convention was that we took the counterclockwise direction for the torques, internal torques, as the positive direction, right? But we ended up getting a negative value for the twist, and therefore point A is actually twisting in the clockwise direction with respect to B. So if B is fixed, the twist of point A would simply be equal to this, right, in the clockwise direction. But B is not fixed, it is meshed with gear C, and therefore we're going to have to find the extra angular twist that comes from the angular twist of point C and then add it algebraically in order to find the net angular twist of point A. So this is where we consider the second important relations we derived earlier. Gear C rotates in the counterclockwise direction because we got a positive value here, right? And therefore gear B must be rotating in the clockwise direction. So if I call this as phi C and this as phi B, there's a relationship between the two, right? The distances traveled must be equal to each other. So here is the rest of the analysis. So I get a value of 0.891 degrees for phi B, which is in the clockwise direction. So if I were to stick to the same sign convention, which is counterclockwise rotations are positive, then that also will be negative, right? And therefore the net angular twist of point A would be phi AB plus phi B, which is minus 2.7 degrees minus 0.891 degrees, which is 3.6 degrees clockwise. So that's it. We answered all of the questions. Just keep in mind that in comparison to a normal single shaft torsion problem, here we had to employ two special relations. One has to do with the relationships among the torques and the radius and the internal contact forces between the two gears, right? The other one has to do with the relationships between the angular twist of the two gears that are meshing with each other.